Welcome to another exciting microcontrollers lecture here. I hope you guys all had a good break. I had a lot of fun. I got a new piece of hardware, which I'm going to describe for you, and it will help us with our little touch-tone synthesizer project, which I thought would be fun. So what I did was I hooked it up to the output of my dual tone multiple frequency generator. And what you can do, I think, if I turn up the volume, I like to keep it down because it's annoying. So I guess you can hear that, right? So it's decoding it. I'm going to move this wire here so you can see what's going on. Yeah, it's decoding it in real time using a little chip. And the little chip, this is a board I got on Amazon for the decode so that we could see that it's actually able to decode in real time. And then I made a modification to my program so that what you could do is you could turn a knob and speed things up a little bit. And my question was sort of, I wonder how fast we can push it before this chip gets swamped. And you guys can hear this, right? It's really annoying.
Yeah.
But it's working, right? So you can sort of see it counting up through the different numbers. And it's still able to keep up. So it's working pretty fast. I mean, that's faster than I can dial. And this is a digital data communications problem, right? Because you have to be able to decode the different symbols quickly. And at some point, what will happen is it gets out there to the point where it can't keep up. And there is about there right there. So he got stuck. He can't decode it. It's going by too fast. And of course, I can play it way faster than that. He'll kick in again. As soon as it gets a little bit slower, now we can start decoding again. So therein lies an interesting problem. How fast can you decode these signals and still get useful data out of it? And I just, I couldn't resist speeding this up to the point where the thing breaks, because I like to test the corner points on these kinds of engineering problems. And that's a real, analysis slash synthesis problem, right? So if you think about it, what you're doing with the DTMF generator, this is synthesizer, so that's synthesis. But this little chip in here that's sitting in the decode facility, that's actually doing the analysis. And that lets you do embedded control. And one of the things you can do, I mean, you can not just pass it through plain old telephone service, right? It's not just about telephones. You could take these tones, you could record them on a little cassette recorder and then play them back. That could be your program. And so if you can decode these things at a specific rate through the communication channel, then you essentially have established the data rate. And this lies what I would call the theoretic channel capacity of the system, given the way in which we're doing our encoding. And so that's an interesting discussion in and of itself. And so what I did was I prepared a little bit of a lecture here on the DTMF synthesis and analysis, because I thought it was just so interesting what we were doing here and so relevant to other courses like communication systems courses and the like. And so this is what we're dealing with, right? We've got our typical Arduino doing the synthesis. We've hooked it up to our little DAC. And then I took the DAC output and I just hooked it to the input of our little DTMF analysis chip. So the analysis is not being done in the Arduino at all. Although in theory, maybe you could write a program that does. That's not doing it. We're doing it in hardware. And so here it is with the lights on. And you can see the little chip with the lights. When the lights on and the contrast normal, all the LEDs kind of blur into one another. And this is a totally cheap little board. You can get them cheaper off of eBay. I bought one off of Amazon. I think 2 of these boards cost like $6.50, and it just seemed like a fun thing to try. And you can see over in here, the output, one of them goes to my speaker, and the other one goes directly to the input of the board. I think that's the advantage of having a little board instead of buying the chip and wiring it up, because you can just plug straight into it because it's got a handy port. And then all it needs is power. The ground comes in from the shield on the little headphone jack. So I didn't even bother wiring that up. I was surprised. You can see the black cable is here because I was ready to wire up ground, but then I realized, oh no, it's getting ground from the audio input. So that was cool. And what I did was, you can kind of see the modification I made to the code. What I did was I measured the potentiometer over here. That's A0, that's my input. And then I took that sensor value, divided it by 10, and used that as my duration, which went in divided by 1,000, and that became my new symbol rate, my baud rate. And so that baud rate represents how many different tones you're getting per second, which is really different from the bit rate. Bit rate and baud rate are different, and they have to be, right? So in other words, if you're in the Arduino, let's see if we can get the port going. Yeah. So here's the port, right? And what we'll do is we'll look at the monitor, and then what we'll do is we'll see if we can get. I don't know what the baud rate is on this thing. I forget. 115,200. Yeah, that's a little bit high. 115,200. That should give us, yeah, bit rate. See, baud rate and bit rate are different. Let's listen and see what that sounds like. That's pretty darn fast. In fact, what we can do as we watch it is, I think we can bring up the well, it must be in here somewhere. Somewhere around here, there's going to be a QuickTime movie, but apparently I can't see it. I don't know why. Maybe because my PowerPoint's in the way. I have no idea. It should be out here. Oh, here it is. I see it's off screen. It's off screen. There it is. So now you can see this is real time. This has not been recorded. And what I'll do is I'll slow things down a little bit. And now when you take a look at the output of the Arduino, you can see he's slowing things down quite a bit. So what we'll do is we'll get both of these things up here at the same time, so you can see what it looks like as we speed things up. So symbol rate, 40 tones per second, is really different from bit rate, 160 bits per second. Why is that? Why should that be? Things will fail pretty quick when we get out there. I think around 64. Yeah, 71. It can't handle it. So you got to be around 62 symbols per second. But the bit rate's quite a bit higher, 248 bits per second. Now, we can transmit much faster, but we can't decode much faster. So that's the maximum I can get this thing to start transmitting, 4,000 bits per second, but it's not decoding it. So it's not particularly useful with this chip, although maybe we could find something that's a little bit faster. I got to turn this down because it's driving me nuts. Yeah. So leave it to me to assign the world's most annoying final project because it makes such an annoying sound. But anyway, having said that, It's interesting because you get to see directly why bit rate and baud rate are different, radically different. Why is that? Why should they be different? Any ideas? No takers on that one? No guesses?
I mean, if you have more bits to use, you could decode faster and faster.
More bits? Well, let's put it a different way. When we were doing the symbols, the number of symbols we have is 16, right? 0 through 9, A through D plus star and pound. So if you got 16 symbols and each symbol is equally probable, right, because of how you do your coding, right? This is called channel coding. Then what you will do is you will take log to the base 2 of the total number of symbols, and that'll tell you how many bits you get per symbol. So number of symbols per second is totally different than the number of bits per second, because the number of bits associated with each symbol, right? This is called the Shannon theoretic channel capacity, is equal to log to the number of base 2 of the number of bits. And you get log to the base 2 by taking log of n and dividing by log of 2. So log to the base 2 of 16 is equal to 4 bits per symbol, because 2 to the 4 is equal to 16. Bit rate is not equal to baud rate. And baud comes from Emile Baudot, a French mathematician who was around during the Civil War. So this is an interesting idea, right? Because when we code with tones and we have all these different tones, we need to be able to discriminate between them. If we can do that efficiently, then if we can know how fast we can do the analysis, that's the chips rate for decoding, then effectively we can compute our bit rate, which wasn't particularly fast, but was interesting because we were just using touch tones to do it. Now, obviously, we could have more efficient means of decoding, but I think this is an interesting approach to learning how a communication system works, right? So this is a key element. We have a digital communication system which is encoding touch tones into an audio channel, actually a voice channel, right? Because telephones don't go beyond 4 kilohertz, right? Their sample rate is 8 kilohertz. So you can't go much higher in frequency than that. And you're limited by your signal to noise ratio. But here we're not actually limited by that. We can take the output from our Arduino and plug it directly into the chip. And that gives us a theoretic maximum baud rate, because we know our chip can't go faster than that. Even, well, assuming our connection to the Arduino is noise free, and pretty much is relative to a phone system. So when we think about like our Arduino outputting these different frequencies, we can see there's low tones, right, from 697 to 941. And clearly we could have gone lower. And then there are high tones from 1209 to 1633. And we couldn't have gone much higher, although we could have, I suppose. I don't know. Probably you could go all the way up to something close to 3500 hertz. So if we wanted to, we could have created a new touch tone system that used many, many more tones. But in fact, what we have here is a DTMF system, so that when you press the 1, you not only get 697 hertz, you get 1209 hertz. You got to have both. So the first thing you want to do is you want to discriminate between low tones and high tones. How do you do that?
How do you mean, like, discriminate?
Well, how do you separate the low tones from the high tones?
You would filter one of them out.
Yeah, you get a low pass filter for the low tones and a high pass filter for the high tones. And then you have to build a detector for each one of these tones to figure out which button is being pressed. That's how the analysis is going to work. So when we look at something like, I got to get this shtick out of the way here. I don't know how to do that. But anyways, do you see the zoom controls on the top? Are they being digitized?
No.
Good. Okay. Then it doesn't matter. I see them, but you guys don't. So here's what happens when you change your duration, and you don't have to do this, okay, for your final project, but I did it because I just wanted to know what was going to happen when my little analysis chip failed. I wanted to, explore the corner points and the various bit rates. So what we're doing is we're taking our high frequency, and we're running it at maybe 1/50th of a second. And the reason I say that is because if you have a baud rate of 50 symbols per second, you can apply that to the different numbers that are being generated. So with the high frequency, 1633 hertz, and that's the case because it says 1633 here in the lower right. I got a low frequency of 697. My highest frequency is 1633. I want to know how many cycles there are in a 50th of a second. So I take 50 and divide it into 1633, and I say, oh, I got 32 cycles to play with in order to recognize that frequency. But now I got to do it again, only for the low frequency thing. And so for the low frequency thing, I got the 697 hertz. I divide that through by 50, and I got to come out with an answer of yes, I see that frequency within 14 cycles. Now, if you think maybe I could have done that faster, and maybe you can, then maybe you could get a faster recognition rate. Now, here is a MATLAB output for the dual tone multiple frequency input. In the top, you see the two frequencies combined. Then at the bottom, you see the low frequency, and at the top, you see the high frequency. And what you're doing over here is you take what's called a fast Fourier transform, and you can see the power spectral density at the two different frequencies, and that will help you to do the identification. And in fact, you could do an FFT on the touch tones to identify the different numbers that are being pressed. And that's a reasonably good thing to do, a Fourier transform. And you might have seen these things if you took an ordinary differential equations class or a linear systems class. You probably saw Fourier transforms, if not fast Fourier transforms. Fast Fourier transforms are just algorithms to help you do a Fourier analysis. And Fourier analysis is just an integral over a voltage as a function of time multiplied by a sine wave and then a cosine wave, or a sine wave with varying phase, two different phases. So it's a correlation between sine waves at different frequencies. And that amount of correlation, that's what you call the Fourier coefficient. And certainly we could have a lovely discussion about Fourier transforms, but that's beyond the scope of my little microprocessors course. If you take linear systems, you'll learn all about it. Or if you take ordinary differential equations, you'll learn about it. Or even if you take biomedical signal processing, you'll learn about it. So that's kind of a thing. FFTs, everybody knows about them. Common algorithm, nice and fast. And I could talk to you till I'm blue in the face about that one. So yeah, you could use FFTs to do the analysis, but that's not what they do in a practical chip. If you record it and do the whole thing offline with MATLAB, yeah, no problem. But if you want it to go in real time, this is not the way to go. So here it comes, the chip. And you get these in different form factors. This one is in a dual inline package. The one I got is in an SO, a small outline integrated circuit package. You count the pins, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's an 18-pin SO IC. So this is going to take the DTMF tones and give you a 4-bit code that corresponds to the tones as they come in. And what's inside of this silicon is kind of interesting. And, it's a little bit of a mystery when you look at the data sheet, exactly how they implemented certain things. And we'll talk a little bit about that, because I think they wanted to keep it like the secret sauce. They don't feel a need to tell you how they implemented stuff. They just want to tell you what the input and the output is. But they give you a basic idea. Also, from an Arduino point of view, it's kind of interesting to do remote control, right? You could call up your home and start typing something in from the keypad, an Arduino can control your house, right? Hit the button and then turn on the lethal burglar alarm that has the remote control spear gun or something. I don't know what it does. So I mean, you could see somebody coming in with Ring, right? Oh no, it's burglars. They're taking my packages. And so you open the trap door and they go into the bottomless pit with the alligators or something. I don't really know what you do with these things. So here comes, I mean, you've been victimized by this, right? Press 1 for English. Press 2 if you don't give a crap. Press 3 if you would rather eat glass than sit on hold for the next 45 minutes. That sort of thing. So there's a chip. This is the chip I got with a crystal. That's a whole other story. They call this a subcarrier crystal, which is used for the old style analog television systems. That has the world's cheapest crystal, and it runs at 3.58 megahertz. And that's powering this chip. And it needs a precise or reasonably precise crystal on input. And you'll see why in a minute. And then this is the tip of the connector. The ring, that's going to be your ground. And then the rest is just some ancillary stuff for showing output like the LEDs. And you would probably wire this directly into your Arduino and measure the tone that's being pressed. So it's really a hybrid analog and digital integrated circuit, truly hybrid. So here is the buttons, right? And here are the low frequencies. And then here's the high frequencies. And now here is the binary coded output, which is what you've been watching as the little blinky lights go by really quick. And so that's kind of what you would be using as your input to your Arduino if you were trying to decode these touch tones using the hardware. So that's not too bad, I think. And then this is what's inside. So now we got the low pass filter, which low passes at everything under 941 hertz. And we got the high pass filter, which is high passing everything above 1209 hertz. And so here's the high group filter. There's the low group filter. And somewhere in here, there's a thing called a dial tone filter. And dial tones are around 400 hertz. I forget the frequency exactly, but you want to get that dial tone out of there. So that's like a little notch filter. Notch filters are kind of like an overlap between a high pass and a low pass filter. They just knock out the one frequency that you don't want. That's what a notch filter does. And dial tones come in at frequencies that we recognize. I think they're 400 hertz or so. So that's the shtick. That's the chip. They don't tell you what the digital detection algorithm is. They don't tell you how the filters work, and they don't tell you what is in these little zero crossing detectors. But we can guess. We can guess what's in it. So here's a little blow up. They call this a switched capacitor filter, right? And that's filtering out 440 hertz. That's going to be, well, it's a concert A. I guess that's what your dial tone is supposed to be. Maybe 350 to 440 is the range. And that gets taken out by this thing called a third order switch capacitor filter, which notches out these two frequencies. And then there's a 6th order switch capacitor filter and another 6th order switch capacitor filter for the high pass and the low pass. And so then your next question is going to be, what's a switch capacitor filter? Does anybody know what that is? You guys, have you guys seen that before?
Well, I know what a capacitor filter sometimes is like used for filtering out certain, like shorting out like certain frequencies.
Well, you've heard of RC filters, right? Resistor capacitor filters.
Right.
But switch capacitor filters are different. They're just like, well, RC filters. And the difference is they're switches, just like you might imagine. So S1 will close while S2 opens, and you'll never have S1 and S2 open at the same time. And then S2 will close when S1 opens, and you can control how long this capacitor under the switching is going to be used for charge. So this is the basic idea. I'm not going to teach people how to design switch capacitor filters. I'll leave that to the active electronics course, but you should know that these things exist. They enable you to tune the filters dynamically. You can change the capacitance, the amount of time you spend charging and discharging, and that enables you to alter the filter actively. So this replaces an active RC filter using what's called a reduced form factor. That means smaller and higher accuracy and tunable filter, because you can control these switching rates. In fact, if you wanted to be really clever about it, you could write an Arduino program with a little analog high-speed switch, 4079 or 4069 analog CMOS switch will actually allow you to build these things discretely if you want to. So you want an analog switch in here to charge and discharge your little capacitor and control it. And that's what a switch capacitor is. That's it. That's all there is to it, except, well, the design part, which is beyond the scope of this lecture. But that's what's going on inside. If you wanted, you could buffer it with a little op amp, and then there's this little feedback capacitor. And what you're really doing is you're changing the effective capacitance of C sub S, the switch capacitor. And so that is active switch capacitor filter right there. And there are some interesting, for simple designs like this, there are some fairly simple formulas. When you're done building this whole thing, what you get is a frequency response curve, which corresponds to this little guy. And so now we can look at what's going on. This is right from the MT8870 data sheet. X and Y, these are the dial tones. That has to be filtered out with the notch filter, but you can see what happens as you get to those frequencies. You get severe phase shift and distortions right in through here. But we don't really care about that. We just want to knock out those frequencies that are below 440 hertz. And then over in here, we have a nice flat filter, really tuned so that it will respond and say yes to frequencies A, B, C, and D, which are your low frequencies between 697 and 941 hertz. Then you got a second filter, and here's like a 1 kilohertz in here. And he's going to say yes to E, F, G, and H. Meanwhile, the first filter says absolutely no to the E, F, G, and H, and kind of gives you a little bit of signal, but mostly not. And you got a nice flat area around E, F, G, and H. And so E, F, G, and H are your 1209 to 1633 hertz filters, frequencies. So that's how that works. You can divide up with a low pass filter and a high pass filter, the two different frequencies, the low and the high group for the DTMF tones. So that's kind of an interesting thing that's coming out of this MT8870. A lot of technology in there that's analog. I mean, it's sort of mixed signal, really, because switching capacitors involves a digital signal, but the capacitors, of course, are analog. And then you take the high part and the low part and you run them into two zero crossing detectors. See, we're not doing FFTs in here. We're counting the number of times. Well, first of all, we square up the waveform that comes out. So sine waves are coming out at different frequencies. We want to turn them into square waves. That's what a zero crossing detector does. You could say, oh, what's that? Anybody have any idea what that could be? Zero cross detector? Any ideas? So it's an op amp that runs from one supply rail to the other. When it's below a certain threshold, it gives you a 0. When it's above a certain threshold, it gives you a 1. And what it does is it takes these nice smooth square waves, nice smooth sine waves, turns them into square waves. That's what it does. It's an op amp. It's a comparator. It's above a certain voltage. It'll give you a 1. If it's below a certain voltage, it'll give you a 0. Here it's inverted, so it doesn't really matter. We really need to count, right? How many zero crossings you have per second. And now you know your frequency. So forget about all this FFT crap. We don't need that. We just need a counter. And we've taken Digital Design 1, so we know how to build a counter. Besides which, I think even the Arduino has a counter built in because, well, one thing microcontrollers know how to do is they know how to count. Plus, 1200 hertz is not that fast to count. So Arduino runs at 16 megahertz. You could easily count to 1200 hertz. I mean, that's not a problem. So that's the shtick, right? Now we've got our little comparator. We got a square wave. And this is how you build a zero crossing detector with a dog breath op amp that you might find in the shop. We've got a pile of these hanging around, the 741 op amp. And it'll go from one supply rail down to the other. And you can use these diodes to help assist, making sure that, well, you have a 7/10 of a volt hysteresis around 0 volts. So these things will just flatten out to the VCC or flatten out to the VEE voltage. And you can run these voltages any way you like. 0 to 5 volts might be okay for your input for your system. So that's how you square up a sine wave. And then there's this mysterious digital detection algorithm. I don't know why they made it so mysterious. It's a counter, right? You just have to count the number of ones and zeros, or count the number of ones in a given period of time, and you'll know what your frequency is. And that's it. That's your analysis. They made this into like the secret sauce. I don't quite understand about the secret sauce. It's not really much of an algorithm, but that's how they label it, and they don't tell you what's in it. But if it was me, I'd put a counter in there and just sort of count. It's a frequency counter. Now, there's another way to do this. You can do it with the bandpass filters, right? You could have 8 bandpass filters, and they all say yes when they see their specific frequency. And that's legit. That's how they started these things. They, back in the beginning. But because the bandpass filters were so big and expensive, they were restricted to the central office, also known as the telephone exchange. Moreover, when you get to the higher frequencies, the plain old telephone system, also known as POTS, doesn't really do very well. So they give a preemphasis, that is increased amplitude, to those higher frequencies. They make them a little louder. That way they can get through. They call that a twist, or preemphasis applied to compensate for the roll-off. That means you don't have good high frequency response in POTS, plain old telephone system. Moreover, the bandwidth variance on these tones could be quite high. I mean, it's plus or minus 20 hertz. So you can get a sort of a 20 or 40 hertz wide, I'll call it bandpass filter for each one of the frequencies. And you can essentially try and build it so you don't have to count the number of zero crossings. But counting zero crossings isn't that hard, especially for frequencies this low. So while this is the way they did it initially, it's not what they do in modern practical systems, because the digital stuff can easily outpace the bandpass stuff. So this is how you build a frequency counter. And that's kind of interesting, right? Because frequency counters are things that you can buy as test equipment. And all you're really doing is building a frequency counter for this one specific application. And it's all on the chip. But you could have done this with your Arduino. It would have been fine. And the only tricky bit would have been the switch capacitor filter, which you could probably also build with an Arduino. So this is a essentially a counting register. You have to tell it when to start counting and when to stop counting, and then you'll know your frequency. So if you count for a whole second and then you stop, you'll know what you counted up to, and you'll know how many zero crossings you have, and you'll know your frequency. And that's it. That's the whole shtick. And then there's this thing about the tip and the ring. And you know what they do in these with these 3.5 millimeter stereo jacks is they give you a thing they call the sleeve. So this is a TRS, tip, ring, sleeve connector. And between the tip And the ring, you get the left channel between the sleeve and the ring, you get the right channel. There's another variant on this called the TRRS for tip ring sleeve. And that'll give you the ability to have a microphone as well. So a lot of times what will happen is you get, something for your iPhone. It's got a tip ring sleeve because it expects to be able to talk to the, have you talk into the iPhone as well as listen. And that's it. That's the whole shebang. That's the long and short of the decoder chip. And I just thought it would be interesting to try these things. I just got it over the weekend. I got so excited about it. I prepared this little lecture. And what you can do, if you go back, MT8870, you can actually Google the data sheets up on that stuff. Let's see if I can grab MT8870. And there's the chip. And here's the board. There's the board. Here it is, $1.33 on eBay. What a bargain. And then you can use these outputs and you can actually plug this straight into the Arduino input. So if you wanted to, you could see the Arduino plus the MT88 plugged in. So it actually has its leads, so it can plug straight in here, get its power and ground, and give you a digital input to your Arduino for that application. Boy, that seems like it's worth a couple bucks. Save you all the wiring. And you can get these things, as I said, much faster if you go through on Amazon. Here, Amazon will give you 5 pieces for $8.99. So that's a cool little gizmo, and I never had my hands on this before, so I just thought it was a fun thing to have. If you were thinking about ways in which to do automation remotely via telephone, I mean, you could do worse than dual tone multiple frequency control. And I don't know what the applications could be. I used to be a chief engineer at a radio station, and we used DTMF to control the transmitter. You could turn on and off tower lights. You could turn up the power. You could turn up the plate voltage. You could do all kinds of interesting things remotely using DTMF decoder. So that's kind of an interesting idea. You could measure power. You could, dial something and maybe it plays back through voice, something like the wind or temperature at the remote site, stuff like that. So you got an opportunity to do all kinds of embedded control systems, and with the DTMF. Let you imagine you could control a robot, right? And left, right with little touch tone controls. Maybe, I don't know what you'd like to control, but imagine the robot is so far away that you have to phone it up, right? It's not like less than a kilometer where a radio can reach it, but it's more like on the other side of the planet. Well, dial a phone and have it respond to the DTMF controller. And you can put it into the kill, crush, destroy mode and then hang up. So there you have it. The DTMF decoder. What do you think? Pretty cool, right? Lots of applications. How exciting. Well, if you're not excited by this, I feel bad for you because it doesn't get better than this. I was very excited. So, yeah, we've got this this little DTMF project that we have to do. And I was busy trying to kind of make it into a separately compiled thing. So I came up with my own little class for the DAC. And I figured, if you change the DAC, maybe what you would do is you would keep the class DAC, and then you would have some sort of a means of polymorphism, like an interface. And so here's the DAC implementation. And I kind of like this because, it isolates the complexity, right? If your only interface is this, you don't even know what pin number it's on. you could have made that an argument, I suppose. But in fact, you don't even know what kind of DAC it is. Could be any kind of DAC. Could be that R2 DAC that the fellow used initially. So I like the idea of having sort of like a different implementation. So later, you know, if somebody said, oh, I really want a 12-bit DAC, you could overload this operator and have it so that it takes an int instead of a byte, because ints in ints on the Arduino IDE are generally 16 bits. But you could get an unsigned 16-bit quantity too. So that in and of itself, I thought made the code a little bit cleaner, because it takes out the DAC and encapsulates the complexity and gives you a really simple interface. And then here's the DTMF code. Now it has its own sort of interface that looks relatively simple. Generate output, wave generator. And then when we go and we look, we begin to see, you know, maybe this isn't the right thing to have done. Maybe we should have put in a 7 in here. Sometimes we look at other people's code and we say, oh, what the heck is this guy doing? And as I was going through this, I said, well, I don't know why he makes you look this up in some sort of ASCII table, because that doesn't make a lot of sense to me. So this is why I decided that if you use the literal quote hash, or octothorpe, if you like, that's the proper name, you know, you don't have to actually look it up because the compiler will do that for you. And in fact, if you think about it, you could extend this system to use non-standard frequencies and non-standard codes. But for now, I think it's very nice that you can find convenient decoders that have been commoditized into relatively inexpensive hardware. And that sort of makes it nice for me, I think. So that's how I would rewrite this code, just to make it a little bit more readable, and certainly doesn't change the speed at all. Now let's see, we can see the different sort of frequencies that are coming in to the columns, and that's fine. And now here comes a wavetable. And I looked at this wavetable and I said, you know, what's the wavetable size? 200. All right, what would it have taken for me to generate this wavetable using sine? And it really wouldn't have been that much, right? I mean, this is like for integer I equals 0, while I is less than 200, I plus plus. And now, in principle, you could have said something like wavetable of I guess you use the square brackets, is equal to the sine of I, and you want it to range from 0 to 2 pi. So divide it through by 200 and multiply it by 2 pi. And then since that's 200 and the other is 2, I would turn this into 100 and get rid of this 2 over in here. And then you want it to range from, right now it goes from -1 to +1, so you say 1 plus, so now it's going from 0 to 2, and so you want a number that goes from 0 to 127, so take the whole thing, multiply by 1/2, and now it goes from 0 to 1, and then multiply the whole thing by 128. Is that the maximum number here? 128. Yeah. So in principle, you could do it by 256, but just multiply by 128 and forget about the divide by 2 over in here. That'll simplify out. And so that would be an equivalent way to set it up in a for loop. that's my way of dealing with these sorts of things. I don't know why anyone would feel the obligation to type in these numbers. That doesn't sound like fun. Does that sound like fun to anybody? Who types in those numbers? That's crazy. You don't do that. Maybe you can cut and paste them from a program that you write. But if it was up to me, I'd put this right here into the setup. And that would be a way in which to address the issue of having an embedded wavetable, especially one where you might want to increase the number of samples, right? Your wavetable size doesn't have to be limited to 200, or you can make it smaller. And I mean, it doesn't really matter. It's just, this doesn't strike, this is like a bad smell, I think. And so, you know, if you do change the size of the wavetable, then you have to take into account the rate at which you're clocking the wavetable out. And so that's an issue. But in fact, I just say this is not the correct way to make a wavetable. It's a matter of taste, I suppose. And let's see what else we can do in here. So now the case statement, the char 1, is doing a dispatch off of 49, right? This literal is essentially the same thing as 49 over in here. So in other words, in principle, if you put char 1 over here, it's no different. It's the same thing. So why create the extra thing? And the answer might be, well, because we have this over here. But then again, you could back substitute that. Right? In other words, this will compile just fine. What did I do? Unsupported board. I got the wrong board selected. My bad. I probably had this set up for a micro. Yeah, I did. This has got to go to Arduino AVR board Uno. Yeah, it works now. Yeah, the micro uses a Atmega 32U, which is a slightly different chip. And I've got this in the, how you say, in the macro. So if you were to upload this now, you should be able to get the annoying sound coming through. I don't know if you can hear that, but annoying sound. So there's the annoying sound. So in principle, your generate code, let's see, where was it? That's it, your DTMF code. You don't really need these characters to be embedded here. I mean, you could have written this as char A. And written this as char D. And then A and D, you know, you don't even need this, right? You could have just written, look, if you want A, put A in there. If you want B, put in B. You know what I mean? You don't need the extra level of indirection by writing out char hash. The switch can take it. So it's a bit of refactoring, I think, but it kind of needs the refactoring because, well, in principle, let's see if this still works. Yeah, that still works. So in principle, you don't need any of that stuff. So this whole thing with the A and the B, I think I can comment that one out. Right? He doesn't need it. And so if you were to comment out something like this, the C, you can just copy it, and everywhere there's a problem, paste it in. So here's C. And that's done. So that's my point about this code. It just seems like something wrong with this guy. I don't know. Take the hash thing, turn it into a hash. Take the 0 thing, turn it into a 0. I mean, no kidding. Why would anybody want 0 and hash to be written as variables practically? And here's hash. I think I got all the instances of it, but I might be wrong. I missed one. Oh, yep, here it is. And what does that buy you? Good, right? So, I mean, we could do the same thing with 9 and with star. I mean, this code needs refactoring, no doubt. But sometimes it's easier to refactor code than it is to rewrite it. So this is 9. It's a star. It should all work. Uh-oh. Oh, there it goes. So that's all working. And, you know, from my point of view, I think it makes sense to try and get rid of some of these embedded things. I really don't see the need for them. Just comment it out, try and do a compilation, and everywhere you see it, just kind of paste it in. I don't think it's in too many places. That's it. And you could do that efficiently, I should think, if you were to just do a copy and paste. In fact, now that I'm sitting here, I could probably do the rest of it real fast and get rid of the reference to all of the characters at the top. I mean, doesn't that make the code seem easier to deal with?
It would be nice to write it your own.
Yeah, I mean,
scratch.
you could. There's probably, I mean, is there a better way to have done this? One thing I can tell you is that this kind of a lookup is a terribly efficient way to go, because key is now being used as a computed go-to by any compiler worth its salt. It'll create a table that'll essentially take the key and these numbers and compute offsets into addresses, which will set these variables. So that's kind of a nice way to go. We could probably comment out all the rest of the numbers now. So I missed something, which I may well have done, actually. I think in the if statement. No, I got it all. So I think the code just got a whole lot simpler. May have taken out at least 16 lines. So that's all working. So in principle, this all becomes garbage. So that makes life a little bit easier. Makes the code a little bit more efficient looking, a little easier to read anyway. Let's see what else we need to know. And any questions about this code? How about that setup? Is that going to make our code slower?
In the setup, yeah, but in iteration, no.
No. Right. So in theory, if there was an initializer for this DTMF, you would be able to do that in the initializer. So that looks like the initializer right there. That's your constructor. So what I would do in a case like this is get the wavetable and set it right like that. Nice and neat. And then the rest of this, I guess you could just, well, I guess we would comment it out starting from here. And ending perhaps over here. Oops. And then somewhere in the in constructor, perhaps over here. What could possibly go wrong? Well, this is going to be a floating point number, isn't it? So we've got to find a way to round it. I'm guessing round is a good way to do it. Only you probably have to spell it right. I don't know if that works or not. What could possibly go wrong? Well, I've left the original code there in case things messed up. Oh my goodness. It compiled. Let's see if it works. I kind of wrote this off the cuff. I didn't really think about it very much. So it might not work at all. Well, that's really cool. I like the way that sounds, but it doesn't sound like a sine wave. I'm wondering if maybe I should give it a little more headroom. Let me just think about this. I goes from 0 to 200. 200 over 1 is equal to 2. And 2 times pi is 2 pi, so that's good. So we're going from 0 to 2 pi, generating sine waves that go from -1 to +1. We add 1, that makes it go from, oh, this makes it go from -1, and it makes it go from 0 to 2. And then if we multiply by 126, it makes it go from 0 to 2 to the 6. How about we take 126 and cut it in half? Make 128 in half is 64. So let's call this 63. I think that's all right, because the wavetable is only supposed to go from 0 to 127, I think. A little error in my logic. This is what happens when you do these things live. There you go. Sounds good. So that's working. So the whole wavetable setup thing was just done when you initialize the class, which means you don't need any of this. And that's how you make a wavetable. In fact, if you think about it, it doesn't really care if it's a sine wave or a cosine wave, right? They're the same wave. So that should work too. And that makes life a whole lot easier because you can now change the shape of the waveform. If you wanted to, you could use tangent or something bizarre, I suppose. Right? Sine waves sound just like cosine waves. As well they should. I'll put that back. So that's my shtick on that one. We wanted a table. I'll write documentation. Ranges from 0 to 127. So in principle, maybe you could get a little more dynamic range out of this. I'm not quite sure if it'll sound distorted or not. I don't want it to go to 128. But I don't think it's going to quite make it to 200. The selected serial port does not exist. The selected what happened? The selected serial port does not exist. No. Don't do this to me. What are you doing? Tools. There it is. It's right there. I can see it. I mean, it doesn't exist. Your board is not connected. Your board is not connected. It can't be because I typed a 4 in here instead of a 3. That doesn't make sense. I think I'll reset my little Arduino, and then I'm just gonna see what's going on here. I broke it. How did I break it? The selected serial port is not connected. What? This was working 2 seconds ago. Okay. Life in the big city. So this is a very nice practical example of why you should never do demos live. I'm unplugging the serial port, the Arduino, and I'm going to plug it back in. So I've unplugged and plugged. Let's see if that helps us. That's an Uno. That's the right serial port. If this doesn't work, I'm switching USB hubs. Oh, look, it's working. So I unplugged it and plugged it in, and now it's working. See, this is not a valid problem in computer science. Let's hope this works now. Yeah, that works fine. All right. So before I got distracted by my Arduino falling off the edge of the amount of voltage that my little USB hub can drive, I probably have too many things plugged in. What with the camera and the other shtick. Let's see how this sounds. Oh, got buzzing. I got buzzing. I knew I would. All right, so there you go. That should be fine now. You can understand why the buzzing happens, right? Because if you go over the dynamic range capability of the DAC, you wrap around. So this should sound okay now. Done compiling. Did it upload? I must have clicked on the wrong thing. Let's see if this works now. Yep, it's all working. Very fun, very fun. So that's the shtick. Any questions about the code? I can get rid of this thing now. It just got a whole bunch simpler, I think.
Professor.
Yes.
If you were to use, you said cosine and sine sound the same since they're only shifted by a phase of 90 degrees or a phase of pi.
Yes,
What
sir.
would happen if you use secant or cosecant?
that a built-in function here? I don't think we have that. We'll
Would it
probably
work
have
if you just did 1 over sine or 1 over cosine?
I mean, I could try it with tangent. I don't think it would sound very good. Let's try this. Right? Because aren't there asymptotes? And the asymptotes are little pokey things, and they're going to sound real pokey, right? Because they go up real fast and they make little sharp edges, and you're not going to like the way that sounds. But let's hear it anyway. I can call the operator with my pocket calculator. Toot, 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 toot. Yeah, this is like a Kraftwerk thing. I actually like it. Yeah, I don't actually. Here's the question. What do you? Yeah, see, the DTMF system can't deal with it because from the decode point of view, it's a big lose. You can't. I mean, he's stuck. Put it that way. Just stuck. We'll do a let's shrink it down a little bit so you can see what's going on out here. All right. So you see, he's not actually able to understand this thing. He's stuck. He doesn't understand about the tangents. Okay. The whole thing was designed for sine waves. If you want to decode, you need to generate like sine waves or cosine waves. Now, if I were to go back and change this from tangent to cosine, then you'd have something. Let's hear it. Yeah, now it's working. So that's that. You don't see it very well because I've turned the contrast way down. I've got to turn this down here because that's annoying. But if you go to the so-called IPVO camera control display, you can change the way in which contrast is handled by going to default. And then you can actually see the device sitting here. There it is. That's the, I don't know if I can bring it a little closer. And you can change the autofocus on it. Let me change the autofocus so it looks, no, it is on autofocus, I guess. So that's the, once you change the contrast, you get a glow from the LEDs that you really don't see when you look at it with the naked eye. But the camera sort of blooms when the CCD elements pick up on this on the LEDs. That's why I turn the contrast down. What you really want is a red lens. You throw a red lens on there and it'll attenuate the output, the red output. So that's yeah, you can do, I mean, any waveform you want, secant, cosecant, I don't know. But this guy, he wants sine waves, right? He's designed a switch capacitor system that's optimized for this application, put it that way. And that's all right. I mean, that's kind of what it's for. If you said to me, well, but Professor Lyon, I really want to have more than 16 symbols. I want to have, I don't know, 128 symbols. Then I'd say, oh, okay, then let's, come up with a new way to do decoding because this may not be a DTMF system anymore. Maybe a system designed specifically for computers to communicate with computers. But here's the interesting thing. If you took your program, just this program, and you encoded it using a 4-bit symbolic system and then turned it into touch tones, you'd be able to store it onto audio tape, put it on a cassette, and then take it with you and then play the tape back And then this could decode it and you get back to your original program, right? You can store your programs now on magnetic tape, on audio tape. So that's kind of neat. Or you could send them through a phone line. And unless unless the National Security Agency has an echelon program designed to decode touch tones and get back to your original code, and they may not, you should be reasonably secure, right? I mean, you've got a kind of an in-band mechanism for, yeah, we're not doing the R2 network anymore, for doing the transmission of digital data. So that's pretty cool, right? Any questions about this project? Anyone start the project or get stuck with the project? Because I the more I look at this project, the more I think, there's a lot of, I'll call it, I don't know, subtlety involved with the code and with the way in which the system has been put together. So it makes for a very interesting project, I think. And I think you'll have a lot of fun with it. So that's what I have for you for today. Any questions?
No, thank you, Professor.
Thank you. Enjoy the rest of the day and stay safe.
You too.
Thank you.
Thank you, Professor.
Thank you.